we have the potential for a direct addition, 1, 2, or an indirect or conjugate addition, the 1, 4 addition. And remember, the 1, 4 addition is the one that's tricky because it looks like a 1, 2. But because our intermediate is actually where the 1, 4 is identified, the enol intermediate that rearranges, or not rearranges, but tautomerizes and takes us backwards, it still looks like a 1, 2, but it's officially a 1, 4. Okay. And that's where we're then getting our subdivision out into our strongest nucleophiles, which is what most of Chapter 17 was looking at. Our hydride and our carbide nucleophiles, if you will. The tail end of Chapter 17 brings in this concept of the Gilman reagent. Okay? And that's really where the conjugate addition sits for the moment, is just looking at the Gilman reagent and the end of Chapter 17. Chapter 18 then takes us to our strong nucleophiles, and that's our oxygen and nitrogen nucleophiles. Right? So, I wish I could say I remember why I have this review slide here. I don't, but it's good because you should review these. You should be able to identify all of our reactions. Okay? This is something you need to be able to do. If you can zero in on what type of reaction it is, you can help you with your reagent understanding and remembering. Fudge monkey. So let's take a quick break because, you know, I've only been talking for 2 minutes. And look at synthesis. Okay, so let's go back and review our synthesis. We will be bringing that synthesis activity back again. Okay, so that is going to come back again, but let's take kind of a quick minute to go through and look at some methods on these. So when we're thinking about synthesis, kind of identify some big things. These are the big things that I would recommend that you focus on. Okay? Identify your changes. Okay, so what are the changes that we see in this reaction? So you see no changes. It looks exactly the same on both sides.
The pi bond changes location.
Okay. So pi bond changing location, I would like you to use different wording, but I'm okay with that. What's the different wording?
Rearrange.
I don't even want you to say rearrange.
Pi bond breaks and then another one.
Pi breaks, pi forms. Okay. What else?
The carbon gets hydrogen.
Say that again?
The carbon gets hydrogen.
Carbon gets a hydrogen. What do you mean?
The one that's originally double bonded, it gets another hydrogen.
Okay. We're making that hydrogen bond. I'm just going to say H make. Is that the one you were talking about? Is there another one?
The one next to it.
Okay. Both of those are getting hydrogens. What else?
You're losing hydrogen when you're moving pi bond on each of the carbons.
You're breaking both of those. Right? So we've got a lot of individual changes going on within this. Again, with our pi bonds, I would make kind of the argument that those aren't really breaking or forming. It's really the hydrogen sigma bonds that are being broken and formed that are causing the appearance of a pi bond to appear to have changed locations. Okay? So let's keep our focus on our hydrogens. Okay? So, okay, does a reaction do all of that? Can I make 2 hydrogen bonds and break 2 hydrogen bonds with a single type of chemical reaction? No. Okay, which means I'm going to need multiple steps. Okay, so let's try and think through how to do that. So let's think about a reaction type that does any of that. Could I make the 2 hydrogen bond? Okay, is there a reaction that would just make those two hydrogens? Technically, yes. You've seen it.
Electrophilic addition.
It's kind of an electrophilic addition. That's where we classified it. That's our reduction reaction, okay, which really was just a straight addition. It doesn't really classify neatly as electrophilic or anything because that's our metal catalyst. We could just straight up add two hydrogens to an alkene. So we could do that. So let's give it a shot. H2, platinum, or palladium, doesn't really matter, or even nickel for that matter. And we would add two hydrogens and we'd end up with that structure. Right? Okay. That makes the two hydrogens in a quick, straightforward addition. Does anybody have a problem with doing that?
We've lost reactivity.
Okay. So yes, we've now added the two hydrogens, but we're now at a structure that has no reactivity. Zero. That's not so great. We could potentially add that chemistry back in, but ideally we don't lose it. We keep it all the way through. Okay. So while that is a possible synthesis, that's not the greatest. Let's try again. Okay. How about breaking the two hydrogens? Was that an easy one to do? Why not?
Because there's, between carbon and hydrogen, there's not much of a electronegativity.
There's no difference between carbon and hydrogen, so breaking the red hydrogens doesn't make sense. Okay? Breaking the reds off, period, either one, doesn't work. Adding both blue hydrogens out of the gate doesn't work. So what can we do? And yes, I used very careful phrasing. Breaking the red carbon hydrogens, either one, does not work. Making the blue hydrogens at the same time does not work.
We should do it in steps.
How about let's look at doing it in steps. The blue hydrogens are by far going to be the easier ones to address out of the gate because the pi bond's reactive. Okay? So let's look at how we could put hydrogens on to that pi bond. Hydrogen is more than likely going to be added how? Charge. What charge would the hydrogen likely come on as? It's likely going to come in as a positive. If it was H minus, it doesn't work, okay? Because that's hydride. That doesn't react with our pi bonds, our non-polar pi bonds. If it was H2, we tried that. That killed the chemistry. Not a good option. Okay? So we're likely adding H plus, which would mean that first hydrogen would go where?
Substitute carbon.
The least substituted position. Our electrons would come out. We'd make our bond to that hydrogen. Okay, and what we're doing is showing our work, our thought process here. But then I'd have a carbocation. I'm not allowed to have that as an intermediate. So what could I put there to replace that? Cyclic intermediate, not going to be so great. Hydrogen's not going to be able to cyclize that.
A leaving group?
How about a leaving group so that we can maintain the chemistry? What would be a good leaving group? Bromine. The bromine would come in as what charge? Negative. Do I have something positive I'm already planning on adding? Yep, maybe what I should add is not H plus by itself, but HBr. That will now give me this intermediate. Cool. I've added one of my hydrogens. That's useful. Okay. I now have a new question. What are the changes? Okay. And because I think think you're getting bogged down maybe in all the chemistry there, so let's just erase all of that. What are the changes?
There's a bromine.
What do you mean there's a bromine?
Bromine attached to the carbon, the intermediate.
So what's the change?
Like being reversible.
Okay. We need to break the bromine off, right, to make this transition. What else needs to happen? Okay. I need to form a pi bond. And remember, forming pies are always kind of questionable. So we'll put that in quotes. To form that pi, what do I need to do? To form the pi, I need to do what?
Oh, sorry.
I need to break hydrogens. And I've got 2 of them that I would have to break off. So I need to break hydrogen, I need to break the bromine. What else has to happen?
Add another hydrogen.
I need to add another hydrogen. Is there a reaction that I can do that will do all of the above? No. Okay, so pick something.
Remove one of the red hydrogens.
Okay, removing one of the red hydrogens. Isn't that going to be challenging? Didn't we say initially that breaking off a hydrogen, a red hydrogen, is going to be very difficult because it's connected to a carbon? It's a nonpolar bond. That's not going to be easy, right? So why are you suggesting we break off one of those hydrogens?
Because now we have bromine, which
Okay.
is a good liquid.
So what I would argue is you're not breaking off the hydrogen, you're breaking off the bromine as a good leaving group. Bromine being a good leaving group gives us that carbocation that's now next to that hydrogen, making that hydrogen relatively acidic, and I can do what?
Form one.
I can form a pi bond, and I have done what type of reaction? An elimination. This has done a couple things for me. That broke the bromine off. I needed to do that. And that broke a hydrogen off. Okay? Didn't get it all done, but at least got some of the things done. Okay? Does that keep chemistry? Yes. Does that keep the chemistry going towards where I want to end up? Yes. So everything about that says, fair game, let's run with it. Okay? So to do that, what do I need to do? Well, we said it's an elimination. How do I get an elimination reaction to occur? Heat and base. Okay? Fortunately, we can't just say add base. We have to be specific with a reagent. What base?
Small.
A small base. Why do we want a small base and not a big base?
Because we want it to go within this.
We want the thermodynamic product. We want the double bond happening inside. If we picked a big base, we'd get the Hoffman elimination. It would take us backwards. So we want a small base. So better, but that's still not a reagent. I want something better. NaOH. What's the problem with picking a small base? Small bases can also act as nucleophiles, which would mean, oh crap, I got to worry about substitution. Do I have to worry about substitution for this one? No, why not? No, the alkene isn't there. That's our final product.
Steric index.
Okay. We picked sodium hydroxide, a strong base, which would mean a strong nucleophile, which would mean what type of nucleophilic substitution? SN2. For an SN2 to be successful, I need a small, sterically unhindered leaving group. I'm a tertiary substrate. That's not going to run SN2. I don't have to worry about the substitution competing. I'm only going to run the elimination. So I've picked a second reagent now. Guess what happens now? Question resets. How do I make that? What are the changes?
Move the location of the pi.
Okay, can a pi bond just pick up and move locations? No, so we said that's bad. We could go through in the breaking of a pi bond, but I've already been yelling at Jenna now twice for that, so she's not going to volunteer that one. Instead of saying breaking the pi bond, let's say, okay, breaking the hydrogens. What hydrogens do I need to break? Ooh, interesting. There's only one hydrogen I need to break off. I've already broken the other one off. What else needs to happen? Okay, I need to add a hydrogen. Okay. Do I have a mechanistic, or not a mechanistic step, but a reaction step that would do that? Acid base places a hydrogen. This isn't just acid base. Okay. Elimination just makes a pi bond. Well, did I do an elimination? According to what I'm looking at here, not really. I started with a pi bond, I ended with a pi bond, so it's not really an elimination. Which then also means it's not an addition. Which then also means it's not a substitution because I don't have a leaving group. Okay. Radical? God, I hope not. Okay. Which means I can't do it with one reaction step. I have to do it with multiple. So what do I want to focus on? Okay. You want to make the blue hydrogen. Okay. For the sake of argument, I'm going to say no. Let's break the red hydrogen. How would you break the red hydrogen off? Is that hydrogen acidic? Why not?
Carbon-hydrogen bond.
It's a carbon-hydrogen bond, but we had a carbon-hydrogen bond in the previous case.
There's no chemistry for
And there's a pi bond right next door, so I don't quite accept that. In the previous case, what did I need? A leaving group. Do I have a leaving group? No, so I can't remove the red hydrogen. If I can't remove the red hydrogen, let's make the blue one. Okay? What charge is that blue one likely going to come in as? We would probably say a positive, which then means this carbon has to be negative. Anybody look at that and say, that's a problem? Why are you saying that's a problem?
There's no like partial positive, partial negative.
I don't quite accept that. We can do a shift, right? If I did that arrow pushing, I can draw a resonance structure. So you're right, it's not a strong partial positive and negative, but I can put a negative charge there. Why is that structure not so great? What's that?
Carbons don't like the negative.
Yeah.
Would be too that the negative charge is on a tertiary
The
carbon.
negative charge is on a tertiary carbon. If I'm going to draw a resonance structure, is that the resonance structure I'm going to draw? No, I'm going to draw the resonance structure where the lone pair electrons went the other direction. Meaning what? Can the hydrogen be positive? No. The reagent I add must have the hydrogen be negative. Where do I get a negative hydrogen reagent that reacts with alkenes? I could get BH3. BH3 is now a possibility to initiate this. Of course, BH3 is a two-step process that would then be followed by sodium hydroxide and H2O2, right? That would put the hydrogen on and put us an OH out there. So far, so good? Okay. Is there another place that I can get a negative hydrogen? What type of reaction am I doing there? An addition. Okay. And you know I hate names, but is this a named addition? Yes, it is. And it's named not for the reagent, but the type of reaction. That's not someone's name.
Oh, anti-Markovnikov.
It's anti-Markovnikov. Are there other anti-Markovnikov reagents? Yes. Those other anti-Markovnikov reagents would be HBr. HBr is Markovnikov, isn't it? With Rohr. Now it does anti-Markovnikov. Right? Okay. Both of those added hydrogen, ooh, 2 pathways. Okay. Being particularly irritating here because we're going to draw both pathways. We're going to keep them on there. We now have 2 possibilities to get to our next thing. What has to happen? Break the bromine, break the hydrogen. Save the world. Sorry, that clicked in my head for some reason. Or break the hydrogen and break the OH. Am I allowed to do both of these reactions? What type of reaction is it? It's an elimination, straightforward elimination, fair game. Okay? Are both of these reagents allowed to do an elimination? So I'm seeing some gritting teeth. Why are you gritting your teeth?
Bromine is a good leaving group, so we can do that in one step.
So bromine's a great leaving group. Okay? So cool. You're probably not gritting your teeth about that. Bromine should do an elimination really straightforward. So what are you gritting your teeth about?
The OH.
The OH is a bad leaving group. Okay? But I could make the OH a good leaving group by adding an acid and adding hydrogen, right? So I could add H2SO4, which would make it a good leaving group. How would I break that carbon-hydrogen off? Heat. Okay. How would I do the other one?
Just
Heat and base. Okay. Base is not an official reagent. Okay. Whoops. So we could try sodium hydroxide. What's the problem with sodium hydroxide? It's a strong base, yeah. It's also a nucleophile. I have a secondary substrate that could potentially become a problem. Okay. Take it a step further. In that one, to do the elimination, what is getting eliminated? The bromine and hydrogen. The hydrogen from which position? You can do better than second. The beta position. Is there a second beta position? Does that second beta position have a hydrogen? Yeah. Okay. Can I prevent that second hydrogen from getting eliminated? How? What happens if I use a really big bulky base? Is it going to be able to get in to the purple hydrogen? Probably not. And so I will limit that secondary reaction. So I don't want to use NaOH. I want to use, what's that? NaH, sodium hydride. Oh, actually, yeah, fair enough. Bulky. Yep, totally lost me there, but you're right. NaH being insanely bulky, probably going to pull the least sterically hindered one off. Cool. Are there other bulky bases? LDA. Are there other bulky bases? T-butoxide. Okay. All of those should work to help get us to the official best elimination product. You guys got a question? Yeah, from Sujatha's class,
Yeah.
DBN or DBU is what you're talking about. So I'll add those on the list. Maybe I'll write an exam question with those structures asking about them being basic or not, but that's about it. Okay, so all of those would work. How about with the other one, with the acid, with our alcohol? The acid makes that a good leaving group, so let's say it leaves, we'd have the carbocation. We're just trying to break off the hydrogen. Where would I expect the double bond to form? Purple or red? You really can't tell the difference between those. So let's make it blue. Let's stand out a little better. Blue or red? As a hint, it's not red. Why would the blue one be the primary product? The blue one is thermodynamically more stable. So given the free will of choice between those two products, we're going to get the thermodynamic. Is that the final product I want? No, which means if I did the BH3 reagent, what happens? Doesn't work. I have the wrong synthesis. Okay? So I would need to have gone the Rohr method to get the bromine on there. The bromine will do a better elimination step. Crap, you went the OH, tough. How do you make the OH a bromine? PBr3 will do the substitution where you lose the OH and you get the bromine back to our chapter 10. Okay? So we're trying to identify those changes, putting in pieces, taking a guess. Does that match with the charges that work? Nope. Try another guess. Does that match? Nope. Let's try another guess. Okay? This is what needs to happen with synthesis. Slowly build your way forwards. Okay? Don't try and make it in one jump. As it turned out for that one, I don't even remember now, we had like 4 or 5 steps in that. Okay? And all we did was a double bond just moved like 2 places. Okay? But we had to go through a whole bunch of individual steps. Okay? By slowly working your way through, what are the changes? You can slowly piece that out if you acknowledge what your reaction steps are. If you don't acknowledge what those individual reaction types are, you're trying to do it too fast, you're just going to start throwing reagents at it and you will get it wrong. Break it down into those slower pieces. Bite-sized chunks will help. Questions about that? There's a lot of steps. Okay? So with that, let's get back to the fun stuff, kinetics and thermodynamics. So, what we're talking about is having a nucleophile react with our alpha-beta unsaturated carbonyl. There are 2 pathways that we could go through and run on this. Okay? Labeled, unfortunately, as the blue pathway and the red pathway. Okay? If the nucleophile does a direct 1,2 addition, we'd end up with that intermediate. If it did the indirect 1,4 addition, we'd end up with that intermediate. Right? Okay. The direct has no resonance, so it pretty much just stalls there until we add the hydrogen later on. Okay, so that's waiting for a step 2. Okay. The indirect has this lovely little resonance stabilization, okay, which gets us pretty darn close to where we ended the direct one with the negative charge on the oxygen. We could then add in our second step the hydrogen, and we would see our 1,4 addition. So there's our nucleophile, 1, 2, 3, 4. We did the 1,4 addition. Awesomely color-coded, Mike. Let's at least be somewhat consistent. There's our nucleophile, our hydrogen, 1, 2, 3, 4. Or in our red pathway, the nucleophile directly attacked. Whoops. And we have our 1, 2 addition. Everybody see that? Okay. If we bring this into our energy diagram now, the reactants in both cases are starting at roughly the same spot. If we move through it in our very first step, what would we expect to happen to the energy? You can cheat and just look at the energy diagram. What should the energy of your product be after the first mechanistic step? higher or lower than your reactant? Lower. Why is it lower? Your answer involves pi bonds. There's less pi bonds in your intermediate, so it should drop in energy. Okay? If we go through, I've got these labeled intermediate 1 and 2. Okay, well, what are we referencing there? Okay, if we take a look at our red one versus the blue one, which one would we expect to be lower in energy? Okay, so let's box them. Here's our intermediate. Here's our intermediate. Which one is lower in energy? Why is the blue one lower in energy? There's resonance stabilization. So I would expect my reaction to occur something like this. And actually we're going to ignore the peak of that for the moment. I'll just erase it again. So we get something along those lines, right? Then what happens? We'd move to our final product. Evaluate our final product. Which product is more stable than the other? Why is and the blue is what?
Pi bond is more substituted.
The pi bond is more substituted, so I would expect the blue product to be more stable. It should be lower in energy. Right? Does anybody see any issues that might be coming out of this? What's that issue?
The blue reaction has a lower activation energy, and
So let's hold on the blue reaction having a lower activation energy. Okay? Your statement there is based off of the activation energy that I erased. There's a reason I erased it.
it doesn't matter.
Okay? It's not that it doesn't matter. Okay? Anybody see an issue here?
You get only one product
Why would we get only one product?
because everything about the blue reaction is lower energy.
Everything about the blue product right now is lower in energy. Right? We would not expect the red product. Right? Which would mean, at least according to thermodynamics, the product we get is rhymes with flu. The blue product. Thank you. Our blue product is the one we end up getting. So if we're only getting the blue product, why are we talking about kinetics and thermodynamics?
Because you're not getting just blue.
Because we're not getting just the blue product. Okay? What else is going into this? What else is missing from our diagram that, say, somebody might have erased? The activation energy. Okay? To see an issue between kinetic and thermodynamic products, our lines must cross. So far, they haven't crossed. Everything is saying blue is our product, both for kinetic and thermodynamic reasons. Which means, in that erased section, what has to be happening? The red has to be lower in energy. Okay? Why? So the why that I want for an answer there is an explanation for why the red is lower, not because we know we're looking at kinetic versus thermodynamic. Right? Does that make sense? Okay. Okay. The nucleophile is trying to cancel its charge. So it's going to react with the most positive atom. The closer those two atoms are to each other, the lower in energy the system. The transition state for the red one is lower as an activation barrier because you're putting the largest negative and the largest positive next to each other. That transition state is naturally going to be lower than the blue one, where you're not putting the two most negative or two most charged things closest to each other. There's our crossover. It's in the transition state for that first step. Okay? So when would I expect to get the red product? That would be the kinetic product. When would I expect to get the kinetic product?
Should always get it.
Okay. We might say I'll always get it, okay, which is a fair statement to make. When will I isolate the kinetic product? Okay. Remember, when we talked about kinetics and thermodynamics, we talked about two states that we could vary. Okay. One of them was looking at the reagent, the other one was looking at the conditions, or our temperature conditions. So to get the kinetic, I don't want any energy in the system. So if I want the kinetic product, what am I going to do? Lower the temperature. So when we're looking at this 1, 2, 1, 4 as a possibility, if I want the kinetic product, we're typically running at low temperatures. To get the thermodynamic, what do I want to do? Run at high temperatures so that I can clear that barrier. Okay. The other thing that we discussed was it comes back to the strength. In the previous case, we were looking at formation of the enolate. Okay, the more substituted or the less substituted was the strength of the base. We're not looking at a base here, we're looking at the nucleophile. If I use a really strong, stupidly strong nucleophile, what happens to the energy of my reactant? Why is a nucleophile stupidly strong? Because it is high in energy or low in energy? It becomes very high in energy. So if I use a stupidly strong nucleophile, what happens? It skyrockets upwards for my reactant. Which product forms first? Kinetic. If my reactant energy is so much higher than my intermediate, what happens to that step? It becomes irreversible. So using a stupidly strong nucleophile, I now have an irreversible reaction. The only product I expect would be the kinetic product. If I use just a strong nucleophile, well, now that reactant energy, because of course just saying it isn't good enough. So stupid up there, and we'll just call it strong down here. If I use just a strong one, now what happens? I will still form the kinetic first, but it's now reversible. So some percentage of the time, the thermodynamic forms. The thermodynamic is always irreversible. Once I'm in the thermodynamic system, I'm stuck there all the way out to the end. Based off of equilibrium, Le Chatelet, and all that fun stuff, I end up with only the thermodynamic product. So changing the strength of the nucleophile changes where I attack and changes the resulting products, be it kinetic or thermodynamic. Okay? And a lot of that had to do with that initial, I'm just going to clear all of that away, with the relationship between the reactant and the intermediates. Okay? That gap. The larger that gap, the more likely we formed the kinetic product or the thermodynamic, which had to do with reversibility. If that gap is very large, it is irreversible. How do I get it to be irreversible? As a hint, 2 answers. Low temperatures so that I can't clear the barrier. And really the low temperatures, all that does is just mean I don't have enough energy to clear it. So it's not actually changing that gap. It just says I don't have any energy to move. Okay? Or now we're changing the gap. Stupidly strong nucleophiles. For the thermodynamic, that ends up being a reversible system. And really, this is where it becomes weird. We're not saying the thermodynamic product is reversible. In fact, what we're saying is the thermodynamic product is irreversible, but the only way we make the thermodynamic product is if the kinetic is reversible. What are the conditions that force reversibility? High temperature and okay. All I've been writing is strong nuke. So the temperature, we have kind of weird definitions. Okay? We have high and low. Okay? What's high? What's low? Equally, I have no clue. Okay? The low, for the most part, tends to sit about -78. Okay? That's our kind of default low temperature. High temperature is pretty much room temperature and higher. Okay? What are stupidly strong nucleophiles versus strong nucleophiles? Okay, so we've got some stupid strong ones. Hydride. Anything else? Grignards. Okay. Which is a nice bullet dodge, by the way, by saying Grignard, assuming that's what you said. Wittig. How about some strong nukes? Okay. Whoops. Come on, Mike, color code. Oxides, O minuses are strong. Nitrides. And here's the fun one. Negative carbons. Wait, what was a Grignard? What was a Wittig? So what am I saying when I say negative carbon? Gilman negative carbons. Okay. Enolate negative carbons. Okay. Anybody have an objection to, like, really? Because I do. That sucks. There isn't like a clean line where these elements are stupid strong and these ones aren't. No, there isn't. Okay? There's not even a clean line on these are negative, these aren't negative. Okay? The Grignard is a negative carbon. The Wittig is a negative carbon. The Gilman is a negative carbon. And enolate is a negative carbon. Why is the enolate not as strong as a Grignard? I heard you. Let me draw. You said it faster than I could draw. That's why y'all don't talk right away, right? You're like, I bet you he's going to draw something. There's a Grignard. Here's the enolate. Why is the enolate not as negative as the Grignard? There's a resonance stabilization on that enolate to actually make it not fully a negative carbon, but a negative oxygen. That makes it strong nucleophile. So cool. There I am. Look at that. I'm an awesome guy. We had a negative carbon, and I just told you it's not really a negative carbon, it's a negative oxygen. That's why it's weaker. Okay? Gilman. I got nothing for you. Okay? What's going on with the Gilman reagent? At its simplest form, it's CH3 bound to copper, and officially we have another CH3 there. And we're looking at that carbon acting as a nucleophile. Okay. At its simplest form in the Grignard, what do we have? We have the carbon bound to magnesium, officially bromide. The bond that we're looking at as being reactive is the bond between the carbon and copper or magnesium. What are copper and magnesium? Metals. Both of them, in fact, are metals, which would mean in both cases the carbon is negative. Why is the Gilman's carbon negative less negative than the Grignard's? Come on. Look at your periodic trends. Copper is closer to fluorine than is magnesium. Guess what? Copper is more electronegative than magnesium, meaning the difference in electronegativity is not quite as large, meaning the copper is less negative, or sorry, the carbon is less negative in the Gilman than it is in the Grignard. Well, how much less negative is less negative enough that it reacts and forms the thermodynamic and not the kinetic? Because that would be my next statement, right? Like, where's that line? It's about there. That's about it. We don't get to quantify it. That's the line. It's roughly there. Grignard and Wittig, stupidly strong. Gilman and enolates, not so much. Okay? So you need to memorize that your Gilman will do your thermodynamic, which is our 1,4. The Wittig and the Grignard do our 1,2. You may not be happy with that. I'm not happy with that. I'd like to actually be able to quantify and say that's where the line is. Okay? There isn't a nice line. That line is somewhere in between those two arrows. It's just a spot. Okay? The only reason we know where that line is we've tested it and we've seen that in some cases it reacts one way, some cases it reacts the other. Okay? And we can look at it as a comparison after the fact, but it's not easy to figure it out. Okay? So what we're looking at in all of these pieces, if we look back to pKa's and hydrides, the explanation that I just went through and gave, come on changing the height of that reactant versus our intermediate is really all we're talking about. If we use a hydride nucleophile, that becomes H2. The difference in energy between hydride and H2 is now astronomical. Okay? That huge difference in our activation barrier or in our transitions then means we get only the kinetic product, the 1,2 direct addition. And we can do that based on looking at reversibility and deciding our reactions. Right? So what we're talking about is how we transition between each of those phases, and we can elaborate and look potentially at pKa's. Officially, we should be looking at pKb's. Okay? So we can quantify, but the amount of effort it takes to go through and quantify that exact line is way more trouble than it's worth, and really what we want to sit at is pretty much the table 7.2. Nucleophiles that add reversibly are all listed. When they add reversibly, what happens? Which product do we get? We get the thermodynamic. When they add irreversibly, we get the kinetic. And if we go through and look at our lists, okay, we've got the Grignard up at the top. That says Grignard. We have our organolithiums. Okay, that also says organolithium. We've got the Wittig there. Okay. We have our hydrides as our nucleophiles, and those are it. Those end up adding irreversibly. That gets us our 1,2 direct addition. That is now our kinetic product. And I can't color code to save my life today for whatever reason. Okay. If we look at the irreversible, okay, we've got the oxygens, the nitrogens, all the halogens. Okay. Notice the acetate will also add irreversibly. It's a negative oxygen, so I would argue we shouldn't even be worried about it. But why would we say that one would add reversibly beyond just the negative oxygen? There's resonance, which neutralizes that negative a little bit. That makes reversibility. Okay. Notice that they actually gave us 2 negative carbons. Cyanide ends up adding reversibly, even though it's a negative carbon. Why is cyanide as a negative carbon less negative? Not electronegative, which withdraws some of the electron density into the structure, which means the carbon keeps its electrons. There's another reason. Carbon in, what is that structure? Nitrile. Okay. That carbon is sp hybridized, which means it's more electronegative. It's holding its electrons tighter, like the oxygen and the nitrogen are. The last one is our enolate. And unfortunately, what they did not list was the Gilman reagent. The Gilman reagent is roughly equivalent to a Grignard in that we have an organo structure connected to a metal, but that metal is copper. Okay? Because it is copper, it has more coordination sites, and it will coordinate 2 equivalents of our organic nucleophile. Okay? Kind of, sort of. That is the big part of the end of the chapter. Okay? Gilman is really just saying here's another nucleophilic carbon, but the real question becomes how does it react? Okay? Given the choice, it will do a 1,4 addition, and it adds reversibly. Don't have to be happy, but we do have to accept it. Are you guys accepting it? Close enough. Okay, so predict some major products. That's a bit weird. We're adding those pieces and it looks like they're both 1,2s. Okay, so this seems to go counter to our logic behind how we just talked about this being a 1,4, right? Okay, we did talk about the 1,4 being hidden. What was it hidden behind? The enol chemistry. Okay. When our nucleophile comes in and attacks, we end up putting the negative charge up there. Officially, when we're doing the 1,4, what we've got, or the reason why we called it 1,4, was because we formed this as a product. Now what have we added? The hydrogen and that cyclohexane at positions 1, 2, 3, 4. That's a 1,4 addition. Why does it become harder for students to recognize the 1,4 addition? What functional group is that? That's an enol. And what do enols do? Tautomerize to the carbonyl, making it look like we did a 1,2 addition. Okay. And officially, that doesn't fit the pattern of the 1,2 addition. The 1,2 addition is in reference to the direct addition to the most positive atom, which is the carbonyl carbon. So the red one is our 1,2, the blue one is our 1,4. Okay. So other things that we could look for are 1,4 typically leaves a carbonyl. The 1,2 loses the carbonyl. Okay. Or we could reference the alkene part of it. The 1,2 keeps the alkene, the 1,4 keeps the carbonyl, loses the alkene. Okay. So for that first one, what do we think? Which should our product be? 1,2 or 1,4? Why should it be the 1,2? We're looking at a negative carbon. A negative carbon out of the gate, you should be jumping all over the 1,2. Okay? You should pause for a second and say, is it an enol or an enolate? Well, is it? No. Is it bound to copper? No. It's 1,2. Okay? Next one. Again, trying to identify our 1,2 versus our 1,4. Okay? The 1,4 leaves the carbonyl, so this one's our 1,4. The other one's our 1,2. What's the nucleophile? The what? The O minus. Okay. Again, focusing in on the chemistry. Sodium's there, I don't care. The methyl's there, I don't care. The oxygen, the negative oxygen, is the one that's important. Is the negative oxygen a stupidly strong nucleophile? No, which means I would expect the 1,4. Make sense? Last one. What's our nucleophile? A negative carbon, which then means we should be looking immediately at our 1,2. Me being extra irritating. I switched the order, right? You see that? I actually just copied and pasted. So, but 1,2 being we would expect the first one to come out of this. We'd expect that to be our kinetic product. Before we do that, negative carbon, what should we look for? Enolate? Nope. Copper? No. Okay? Yes.
Would the temperature on that one affect it? Is it specified?
You're right. We do have that temperature coming in and affecting it. The strength of the nucleophile has a much larger effect. Much larger. I'm actually surprised they would run that one that hot. That seems pretty hot for that reaction. Okay. Our Gilman reagents, okay, we kind of talked about them, and I'm just kind of dumping it in here. That's a Gilman reagent highlighted in red. Those of you wondering why I can't walk around, my battery's dying, by the way. So that's our Gilman reagent with the copper. Okay. It's a lithium dialkyl cuprate. Okay, remember how I said that we'll have our R group bound to the copper and we get 2 R groups attached to it. So that's typically how it's formatted. You'll see it in parentheses with the 2 around it. It's again typically run in THF. Again, typically run really, really, really cold. Okay? Why do we need a secondary reagent? Why did we need a secondary reagent with the Grignards? Thank you.
Protonating the carbon.
You have to eventually protonate your carbon. Okay. This will end in the enolate. We don't put the hydrogen officially on that oxygen. We end at the enolate that tautomerizes. We still need a hydrogen source for our carbon. Okay. So we do need that secondary step. Anytime you're using a negative carbon, you will almost always follow it up with a second step of adding hydrogen. Okay? Because carbon is so negative that not only will it act as a nucleophile, it will typically also act as a base. We have to kind of neutralize that base and put hydrogens back on our structure. Okay? So very similar in concept to the Grignard because of that carbon-metal bond. Our big difference is that it's copper versus magnesium, and as we addressed, copper is more electronegative than the magnesium, which makes that carbon less negative. It's still negative, it's just less negative. Okay? That means we end up getting the 1,4, not the 1,2. Okay? And what this is showing is that we had those 2 possibilities, but we favor the 1,4. Make sense? Question? Boop. No. Still no. Now we'd have chapter 18, right? This is another big summary slide that I built. I built it before we switched textbooks, which is why it has a bunch of other stuff on it. Like you'll notice that you've got the Grignard up there. You've got the Grignard, we've got the Wittig. Okay. We already talked about those, so we can ignore that half of it. Really, we're keeping our focus on the other half, the oxygen and the nitrogen side. Okay. Notice, what are we starting with? Not a carbocation. I don't officially accept that. We're starting with the carbonyl, which has resonance to make the carbocation, which is setting us up for an electrophile. So or sorry, a nucleophilic attack. Okay? So we're now looking at oxygen and nitrogen being our nucleophiles. How does that initiate the cascade of the reactions down the road? Okay? We're going to be doing the same type of nucleophilic addition. Our nucleophile attacks, what happens? Nucleophile attacks, what happens? Okay? The biggest issue within this is that these products tend to be thermodynamically controlled. Okay? Which means we have lots of extra kind of issues popping up with those. Okay? Whoops. So, word association game. I kind of like this slide. What do you associate with the word equilibrium? The end of life. Yeah, that's usually what I associate it with. Equilibrium 152, right? Doing all those calculations, all that fun stuff. Yeah, bleh. Yeah. That is typically what people associate. Oxygen nucleophiles and carbonyls center on equilibrium. Okay? Plays a huge role in how the oxygen reacts with the nucleophile. And so virtually every reaction we do with an oxygen and a carbonyl nucleophile, or an oxygen nucleophile and a carbonyl, is in an equilibrium. An equilibrium that we have to decide which way does it favor. Right? Which is not particularly fun, but unfortunately we just have to deal with it. Okay? So, in that process, right, what we're looking with is we just have to do it. Just get there. Beginning to end, do whatever you got to do, get there. But the big thing that you got to worry about is you cannot break your Lewis structure. Don't give me pentavalent carbons, okay? 5 bonded carbons. Bad, don't do it. Okay? Don't break curved arrow rules. Let your curved arrows show you how you move. Don't throw 20 curved arrows into the same reaction. You can't do that. Okay? You can make and break a bond, and that's roughly it. Maybe throw a little bit of resonance in there at the same time, but that's it. Okay? So don't be jumping a whole bunch. Big ones, don't exceed your octet. Do not lose the octet. Okay? The one there is losing atoms, okay? Losing charges, losing lone pairs. You have to be nitpicky, nasty, behind making sure you account for all of your electrons and all of your charges. This section, more than any section, is one that frustrates students because how long the mechanisms become. Okay? And that's because we can only do one thing at a time. And what we'll find is we'll put on a hydrogen, we'll do some chemistry. The next step, we take the hydrogen off. So why the hell did you put the hydrogen on to begin with if you're just going to take it off? Because that simple protonation allowed for the next step to happen. Okay? By removing the hydrogen, it allows for the next step to happen. Okay? So we'll end up doing lots of protonations and deprotonations, but those are what facilitate and allow the mechanism to continue forwards. Okay? Those are frustrating, but we have to deal with it. Always move your electrons from a source to some place that is lacking them. Okay? This does not mean always negative to positive. It means negative, most negative reactive to most positive reactive. H3O plus is a perfect example for this, which I think I've caught enough people doing this that we're okay with and I won't see it again. How does H3O plus react? And now you're like, I don't want to say anything. It removes electrons from one of the hydrogens. The reactive atom in H3O plus is what? Hydrogen. The oxygen is positively charged though. The oxygen also already has its full octet. It can't act as a positive. It can't act as an electrophile because it can't accept more electrons from outside. So it withdraws electrons from within the structure, making the hydrogen, any one of the hydrogens, the reactive species. So just because it's charged does not make it reactive. Okay? The same thing with, say, our borohydrides. So a good negative example. If we look at a Lewis structure for borohydride, the boron is negative. Is the boron the one that's doing the chemistry? No. Boron is less electronegative than hydrogen. Hydrogen is taking those electrons with it. Hydride is the reactive species. So the charge will help signal you to look there, but don't make that atom be the one to do the chemistry. It could be, but it could also not be. So look there, evaluate what it can do, and it may be the very next atom. Make sense? Okay. When you're moving electrons, bonds to electronegative atoms, what should happen? Okay, what we're saying is we're moving an electron from a bond to an electronegative atom. So if I have a pi bond between carbon and oxygen, where should those electrons move? To the electronegative atom. Okay? So you're moving those electrons towards it. Bonds can move to bonds. That's effectively a resonance system. That's why we would use that. Bonds to atoms lacking electrons. That's like carbocations. Okay? And we can move electrons from atoms to bonds. Okay? Don't try to get too fancy beyond that. Keep it relatively simple, and your drawings should work for you. Let the curved arrows solve the question. Okay? Comparing back to Gen Chem, this is let your units solve the work for you. Unfortunately, you have to interpret the arrows. Okay? You aren't given that information. So you have to draw arrows. Once your arrows are drawn, if you followed the rules correctly, you should be able to draw the results that come after. Make sense? Okay. So with that, what's going to happen? We have a big old hint at the top of that.
Using water as a nucleophile.
Water is going to be a nucleophile. So as a nucleophile, what is it going to do? Water is our nucleophile. It's sharing electrons. It's going to attack the most positive. Where's the most positive atom? So there's my arrow pushing. Okay. Next part. Draw what your arrows show. What is the result of that arrow pushing? So far, so good? How about now? It is what my arrows show. Right? Is there something wrong with my drawing? Yes. Make better arrows to fix that drawing. Those electrons need to move up. So you can draw a single arrow and be like, oh crap, I ruined an octet. That can't happen. Okay, you've now identified it. Go backwards, fix your arrows, then you can redraw. Okay? So we would end up with that structure. Now what happens? There really should be two arrows here. Pulling one of my bad mistakes. I'm doing two steps in this one. Does oxygen want to be positive? No. So what does it need to do? Take electrons. Where does it take electrons from? Hydrogen. Where else could it take electrons from? Carbon, meaning? Reversible reaction. Son of a. Yep. Okay. What atom pulled off that hydrogen? Something basic in solution. Okay. You can get away with showing that. If you show me this, now I'm going to freak out. Why? It has nothing to do with needing more electrons. You're showing me an actively reagent, a super active reagent. If there's a super active reagent in there, guess who told you that it was there? Me, at the beginning of the question. Did I tell you it was there? No, don't start drawing it in. Okay. All we're trying to show with putting the B there is that we have something with lone pair electrons that could pick that up. What that something is, could be water, fine. Could be another carbonyl, fine. I don't care. It's something with electrons. but it ain't negative. Okay? What else should be shown as a secondary step? Apologize, Duke, just let me finish this, because I'm talking too long. And Elisa.
The oxygen.
I need to protonate that top oxygen. It needs to pick up a hydrogen. Where do I get that hydrogen from? Can I write H+? Rhymes with show. No, I cannot show H+ because that is a reactive species. That should have been listed at the beginning. So where do I get a positive hydrogen from if not from H+? Okay, couple answers here. I started with water. Water has hydrogen. Let's steal it from water. Cool, that works. Another option, I don't care, something acidic. Done. It's there. Okay, it's now established. You've shown what's happening. What we end up with is this structure. That structure is known as a hydrate. Would we expect this reaction to go to high yields? That's a harder question. Look at that very first step. Is that first step likely to happen? Why not?
Water is very stable.
Water is stable on its own, so we're saying the reactant energy is very low. What else could we throw in there? There's charge. Just one charge? Two charges. That structure is massively charged, which means your intermediate is super high in energy. Is that going to be an easy first step to do? No. How do I make it go faster? That's our cliffhanger. We're stopping.